Hello everyone and welcome back to our series on urban energy modeling with Dragonfly. And hello from the future because this video is made a lot later than the other ones in the playlist that it's a part of. But I wanted to make it because we have a lot of improvements in relation to the previous video of this playlist in which we modeled electrical infrastructure with OpenDSS. And specifically, there's a new capability that has been added to the URBANopt CLI and to the Dragonfly plugin that will essentially auto-generate these electric grids for you. And this is done specifically through an engine called the Reference Network Model, or the RNM, specifically RNM-US engine. And so I want to walk you through how we can actually auto-generate the electric grid infrastructure from our URBANopt buildings and from a couple of other small inputs like a road network, instead of having to tediously specify individual transformers and power lines and everything. And this is particularly useful, especially for people like me who don't have an electrical engineering background. Certainly, I was usually at a bit of a loss when trying to specify these individual transformers and connectors. And so hopefully everyone else on this series will also get a lot of value out of it. And even if you are an electrical engineer and knew exactly what each of the transformers and connectors referred to in our previous videos, this will still, I'm sure, save you a lot of time because it gives you a much better starting point probably than something you can develop from scratch, or at least it will save you a lot of time in tediously having to set up all these power lines and geometries. So all right, so you can see I have here a URBANopt simulation, which is of this example district that's built from footprints, the same one that we've been working with throughout most of these videos here. But if you remember in the previous video, right, we had specified an actual detailed electrical network that we plugged into this DF model, the GeoJSON component here. And in this video, instead of plugging in an electric network that has all those detailed specifications of transformers and connectors, here instead I am assigning basically a new component that you can get in Ladybug Tools 1.6 or above called the Dragonfly Road Network. And it's somewhat similar in principle to the electrical network. You actually see there's still a substation that you need to specify, right? So at a minimum, you do need to specify what the location of the substation is. And obviously, you need to know where the buildings are and have run an URBANopt energy simulation in order to get the electrical loads of these buildings. But that's almost it. Really, the only other thing that you need in order to be able to auto-generate an electric network that meets these needs is the roads that run in between these buildings. And if I turn on this geometry here, you can see it's just pure geometry. It doesn't really have any properties assigned to it. And all it really is a bunch of line segments or polylines. As long as you have that geometry, basically, we can use the RNM engine to essentially generate the full geometry and specification of transformer properties and power line properties that essentially bring electricity from the substation to these buildings running along the street network. And that'll also make sure that all that electric infrastructure is sized appropriately to meet the peak electrical demand of the energy simulation. Right? So this is all that we basically need to start off with. It's much, much simpler than having to specify individual power lines. And you can see that I've already exported this GeoJSON here with this road network inside of it, and I've already executed the URBANopt simulation, the Energy Plus simulation, using the URBANopt SDK and CLI right here. So I have a bunch of results where you're getting a bunch of SQL files, right? We know these had the energy use results within them, right? But we also get things like this scenario file, which you remember we used in the previous video with OpenDSS workflows in order to actually simulate the power flow through the electrical network in this district. So the RNM workflow is very similar in principle, and it's done specifically through this component called Dragonfly Run RNM, very similar to the Run OpenDSS component that we used previously. And right, if we drag and drop this on the canvas, you'll see that there are really only 3 required inputs, which are pretty much the exact same ones as the OpenDSS one. So we need the GeoJSON, and importantly, right, this GeoJSON must have the road network assigned to it in order for this component to succeed. So we have that already, so I'm just going to go and connect up my GeoJSON exported here. We have the scenario, right? The scenario is what we get as an output from actually executing the whole Energy Plus simulation to give us those profiles of electricity usage for all these buildings. So I will connect this up here in order to supply that input. And then really the only other thing that this component needs to run is a toggle connected to the run here. And that's done because it can take a few minutes sometimes to actually run the RNM engine. And I'll just connect this right now, but I'll keep it to false so that I can explain some of these other inputs here. But basically, as soon as I set this toggle to true, it's actually going to communicate with a server that NREL maintains, the National Renewable Energy Lab, which actually hosts the RNM engine. And the reason why this is all done is because RNM itself isn't open source, but it is free to use, at least through this endpoint that NREL has set up. So basically, you do need to be connected to the internet, importantly, to run this component. But as long as you have a GeoJSON that has the road network, you've run the URBANopt simulation to get the energies to the buildings, and you're connected to the internet, you should be able to basically generate an electrical grid infrastructure for any of the models that you create. So I'm just going to go set this to true right now to start running the RNM engine, or specifically this is RNM-US. So it's using a lot of standards that are for the US electrical grid, although those are also related to a lot of other places on the globe. But in any event, while this is running, I do want to explain some of the other optional inputs here that I didn't touch, because more often than not, it's fine to keep these as defaults. But you can see that the RNM engine does have a few things that you can use to customize that auto-generated electrical grid. One of them is this underground ratio, or UG ratio here. So as you can imagine, the whether or not a power line is above ground or below ground affects a lot of things. It affects things like the insulation and how much energy can be lost to the conductance of the ground. And I think by default, the underground ratio is something, I think it may be a little bit higher, around 0.9, so that the majority of power lines are actually below ground, which is pretty typical for, let's say, an urban district. But, in, let's say, a more residential place, you'll have, power lines above ground, which tend to give you good insulation also with that air between you and the ground. But you can customize that using this underground ratio here. We have toggles to note whether high voltage consumers should be included in the analysis, and the default is false. But again, high voltage, like you will need an extremely intense building usually to be able to do this. Right, it usually is some sort of industrial application that would have a high voltage case like this. And then you have the number of nodes per building, or basically the maximum nodes per building. This is the number of points that an individual building can connect to the electrical grid. And more often than not, when the buildings are relatively small, it's going to be one. I think, probably for a district like this, it would be one for all these buildings. And so this default of one is okay here. But if you have much larger buildings, you may start to have multiple connections from a building to the grid. And so you can use this to customize this. But you can see overall, the RNM engine doesn't take that long to run usually. I mean, this was about a minute or so. And again, this involved communicating with the server, sending all the GeoJSON, right, which contains this road network. It also includes, right, just sending the summary of results from our scenario here, right, our simulation that has those electric grid profiles of the individual buildings. But if we finish this whole process, you'll see that we get actually out of this an electrical network, right? And this is actually the same type of object as what we created for our OpenDSS simulations. You guys remember in the previous video, right? We created this electrical network using this component. We got this electrical network out of this. These two are actually kind of one and the same, right? These are both electrical networks. And importantly, I guess I should also say, since that previous video, we've added a few other components that really let you check the properties of your network. Because we found a lot of the times people were, choosing certain types of electrical connectors from the library of transformers without being fully aware of what the properties of those transformers and connectors were. So in the very latest version of Dragonfly, you'll see that there's a new component. I think it's under the Visualize tab here. Yes, and it's called DF Color Network Attributes. And so this component can be used to color basically any electrical network, whether that's from the RNM workflow or built with the OpenDSS workflow that we did in the previous video. You can simply connect that up to this component here, and then you need to connect an attribute that you want to visualize about that network. And you'll see we got a little drop down here called DF Network Attributes here, this little drop down component. And you can see, right, the different parts of the electrical network have these properties like, well, they have names, and they have things like the nominal voltage, the number of phases or phase count. They have the number of wires and the wire phases. And there are even more properties if you look in the Dragonfly SDK, but these tend to be some of the most important ones. And in fact, and nominal voltage is probably arguably one of the first things that people want to check when they've built a network like this. So I'm going to go and I'm just going to plug nominal voltage in for the attribute here. And you'll see that pretty instantly, right? We actually get a visual of what this RNM electrical network looks like. And you can see, right, it's been snapping to the street network here, right? We can see these colored lines are actually, those are the power lines that have been produced by RNM here. And maybe I will just turn the preview off on this geometry here on this road geometry so we can actually see, right? We can see these power lines going from the initial substation and following along the streets to basically serve all these buildings here, right? And we get a little legend here that's telling us what the nominal voltage is. Because this is just the network, it's kind of overlapping with the buildings here, but I can fix that pretty easily if I just pull some Ladybug legend parameters. I just went over to my Ladybug tab, and I'm going to plug in a point for a base plane here. I'm just going to bring up native Grasshopper point, and I'm just going to use this to set the location of my legend to be, let's say, over here. I plug that in for the base plane, and then I plug this in for my legend parameters here, right? And now my nominal voltage legend is off to the side, so I can see that a little more clearly. And let's see, maybe I can just group all this together because this is kind of a bunch of components here that are together looking at these different properties. And I can turn the preview off on this point here. But right, we can see, right, this is nominal voltage. I believe by default this should be in kilovolts is what the nominal voltage properties are specified in. It's the same as what you'd find in the OpenDSS workflows. So if you saw what the specification was there, it's the same. And you can see a lot of these power lines are pretty, I mean, they have a higher capacity around 12.47 kilovolts, right? That's what's coming out of the substation. And a lot of that is going pretty directly into some of these buildings. But along the way, right, we find things like this transformer here, right? This transformer has a maximum, capacity, voltage capacity of 12.4 kilovolts. I shouldn't say capacity; it's a maximum voltage of 12.47. But it's being stepped down from there, and from there we have this orange line, which is a voltage of 0.48 kilovolts in this case. And right, we have another transformer here that's stepping it down to 0.12, right? So you can get a sense of actually what the recommended voltages are across this network. And you can similarly look at, the number of phases of wires. Most of these seem to be carrying 3, although, some of these are just a single wire that we have here. What else? You can actually check the number of wires, basically. So I guess we have the phase count, right? So I guess phases tend to be A, B, and C, or sometimes it's just A. And in fact, we can actually check what the individual phases of the wires are here, right? We can see that let's see, this yellow one is just I guess we can see that there are kind of 3 wires here, but it's really just, these are just, in addition to a neutral one, these are just S1 and S2. The real phases are things like A, B, and C. Again, probably a lot of these tend to have much more meaning for electrical engineers, especially, if this is your first time just trying to understand this, probably the kilovolts and the nominal voltage is one of the most useful things to look at because it gives you a sense of the overall capacity of the electrical lines. But all right, so now we've kind of understood what RNM is auto-generated for us here. Much in the same way that we simulated the power flow through our custom-built OpenDSS network in previous videos, right? We can simulate the power flow through this network that has been produced by RNM for us. So that's what I'm going to do right now. If I go back over to my Dragonfly tab, you'll see that let's see, if I drag and drop this component on the canvas here, right? You can see if I have run this component, this RNM component already, this component is actually now smart enough, this run OpenDSS component will be able to actually run an OpenDSS simulation using the network that was actually generated by RNM for us. And I realize there's no input for the network to this component, but trust me, as long as you've run this RNM component and you plug in the same GeoJSON and scenario files, this will actually be able to simulate the power flow through this particular network that we've just visualized here. So that's what I'm going to do right now. I'm going to connect up the GeoJSON here. I'm going to connect up the scenario. And I could certainly run it for a specific run period, but I don't mind running it for the whole year right now. And part of the reason for that is because we made a lot of improvements to the actual OpenDSS simulation. You'll notice it's going to run a lot faster than in the previous video. So I'm just going to connect up a Boolean toggle here. I'm going to connect this to run. And as soon as I set this to true, it will start to run that OpenDSS simulation. Oh, and one other thing, if this is the first time that you're running this run OpenDSS component, you'll see that we've now actually added something that will auto-install that Python package. You'll see there was just a window that popped up basically that asked for admin privileges to install this. So I said yes to that, and I'm going to hit OK. And now it's actually starting the simulation, the OpenDSS simulation. And this is the part that shouldn't be much more than a half minute now, right? We can certainly see it's already on September, right? It's almost through the whole year. and it is simulating the power flow through this whole network that we've built here. Right, and all right, great, and it's done, and you can see out of this component, right, we're getting the, just like in the previous video, we're getting a bunch of CSVs for the voltages at the building level. We get a bunch of CSVs for the loading on the electrical connectors and the loading on the transformers here. And certainly I could visualize this using the hourly plots that we used in the previous video. That's certainly a valid way to use this. But I've actually added another new component since that previous video that is called, let me see, I think it's under the energy tab here, color network results. And let me see, yes, here it is, DF color network results. And you see that this is able to take any sorts of data collections like the ones that we had imported from the CSV files, and it takes the electrical network and it will color basically the electrical infrastructure with those results. So I'm going to use this right now. Let me go ahead and let's see. I'm going to first turn off these network attributes. I'm going to turn off the preview. So I'm just going to click that, right click on the canvas and select preview off. And then I'm going to now connect up the network here from RNM to this. And then I have to bring in the data here, which is basically going to be the same thing that we did in the previous video. I'm going to bring in this df read OpenDSS result component, drop that on the canvas. And in this case, I'll look specifically at the connectors and the transformers. So I will connect up, I'm just going to hold down Shift, connect up both this component. So that I'm now getting in factors, like 47 data collections for the factors and the conditions of these different elements of the electric grid. And if I connect up, let's say, the factors to the data here, you'll see that it will instantly color, right, those different wires and the transformers with the max loading factor, basically, with those loading factors from the power flow simulation. And thankfully, right, we can see that none of these are really getting above 1. 1 is, right, supposed to be the maximum loading factor. So all of these are pretty appropriately sized here, all of these power lines here. And very interestingly, right, you see that the maximum loading tends to happen on this power line here that's going straight from the substation to the buildings. And from that, it's kind of stepping down a little bit, right, the maximum loading that these other wires are getting, or these other connectors are getting. Right, so you can get a nice visualization at least of what is happening in the power flow of this simulation to make sure that the RNM results make sense and to basically understand how good of a representation it is. I may just do the same thing that I did for this color network attributes. I'm actually going to connect up the same legend parameters here just so I can move the legend off to the side. Yeah, there we go. Now it's not on top of all my geometry anymore. Certainly I can connect up, min and max values here also to customize other parts of the legend. But this is pretty good here. And in fact, you can even use integers for simulation steps and analysis periods. Like let's say if you only want to look at the maximum loading factor in January, I can bring up a Ladybug analysis period component, then make an analysis period that goes from, January 1st, basically, oops, I meant to bring up a panel that has 1 inside of it. And I can make it go from the start month here and end month here. I'll set them both to 1. Right, and this will give me a period, right, from January 1st to 31st, and I can plug that in for the period. And I'm seeing right now this is the maximum loading factor between January 1st and January 31st. And right, we can see it's a lot lower than the max loading factor of the whole year, right? It's much lower than the 0.95. And that's probably to be expected in a condition like, in the winter time, because typically peak electricity demand tends to happen in the summer when all the air conditioning systems are on. However, a really useful application of these types of RNM networks, especially like a study that I find myself doing more often these days, is that you can use an RNM network generated from an urban energy model with conventional HVAC systems, right? So you remember all the HVAC systems here have gas boilers in them, and pretty much all of the, let's see, I think it looks like I'm not modeling detailed service hot water, but those tend to be served with gas fuel by default as well. And of course, also you remember some of the programs we have here, like the restaurants, those have gas stoves and gas equipment in them, right? And certainly over the next few years, a lot of that gas equipment and gas heating systems are going to be converted over to electric. And so you can still use this RNM network that was generated using the electrical loads of the simulation with all this gas fuel boilers. You can use that though, but simulate power flow using a simulation with all electric air source heat pumps and electric service hot water and all of that. And you can start to see, I'm sure you'll get loading factors that are far above 1 at that point. right? And so this helps us kind of plan and understand that if we are going to be electrifying a lot of our buildings, what will that mean for our electrical infrastructure going forward? What may we have to change? And it also helps us design the electrical infrastructure now to be prepared for those future scenarios, because certainly, maybe a lot of these buildings are being designed right now with conventional systems that use gas fuel, but we know right over the next few decades, that's probably going to be changing over to electric. So this RNM workflow can also help us design and auto-generate systems that will be able to meet these new types of electric demand that we'd expect a few decades down the line when everything becomes electrified. So again, I hope this is a big help to everybody using these electric infrastructure workflows with URBANopt. I know this is a very big part of the URBANopt mission, is making these types of electrical sizing and infrastructure calculations much more accessible to a wider number of people. So if there are any more updates on this down the line, you can expect me to make some new videos for it. But that wraps it up for this one, and I thank you guys for joining in this video. And I think in the next one, if it's not another electrical infrastructure video, we'll be looking at some urban heat island modeling with the urban weather generator. So thanks again, and I look forward to seeing you in the next video.